Okay, final notes on the calculation of whole circle bearing. If you conduct the traverse, closed loop traverse, if the work was done clockwise, okay, or should I say anti-clockwise? If the work is done or was done anti-clockwise, that means you travel from 1 to 2 to 3 to 4 and so on in an anti-clockwise direction, you will end up what we term as with internal angles. Okay? And conversely, if you have done it the other way, going clockwise, you will obtain external angles. Okay, so what do I mean by that? Okay, if you look at this figure here, I'm going to start the work from 1. I'm going to go to 2 and 3. So I'm moving in a clockwise direction. So I end up with external angle, okay, at all stations. External angle. Okay. But if we're going to do it anti-clockwise, okay, I'm going to move from 1 to 2, 2 to 3, 3 to 4 in that direction, going anti-clockwise, so I will end up with internal direction. Sorry, I mean internal angle. Okay, so do not get confused when you do your calculations. You cannot mix them up, okay, because well, you can, but you're going to have a fair amount of time trying to sort out what the angles are or were. But just stick to one system. I think that would be the best thing to do. Okay, you either opt for external angle or internal angle. Okay. Now let's move on to how the coordinates are calculated, because we have talked about observing the bearings and calculating the angles or determining the angles, and we have talked about measuring the distances. Now we've got all the numbers that we want now, so it's time to use those numbers to calculate the coordinate. So in surveying, the most common system that we use will be the rectangular Cartesian coordinate, which simply refers to the x and y, or to be more precise, in surveying we call it northing and easting. Okay, and if you notice there, I've written the coordinates of P as northing P and easting P. Okay, there's a system that we use here in this country anyway. Okay, the convention that we use, northing and easting. Okay, in some other parts of the world, they normally express it as easting and northing. Okay, so depending where you are, but over here, in Malaysia anyway, the convention that we use is northing and easting. Okay, just nothing. What should I say? Peculiar about it. It's just a system that a convention, should I say, that adopted in this country. So just be aware that when using softwares, okay, some software will use that, some software will use this. Okay. Okay, now that's a scan image of a map, okay, just to give an idea what we mean by a rectangular Cartesian coordinate. Okay, rectangular Cartesian coordinate simply means, here it says at this corner of the map, the coordinate is 180,000 north, u simply means north. Okay, this is north, and 600,000 meter easting, or T, which means it's easting. Okay, normal coordinate system I think you used to deal with. Okay, we call it Cartesian coordinate system. Okay, so in order to be able to come up with bearings, we have to have we need to know where north is. Okay, so when we have a coordinate system, the coordinate system has a north direction. So when we have a map, okay, when we're going to plot something out, draw a plan, there are a few choices that we can take. Okay, a few north that we can assume, or we can refer to. Okay, it's either there are four. Okay, three actually, because the last one is just an assumed north. Anyway, you can either go for true north, magnetic north, grid north, and lastly it's just an assumed north. Okay, if you don't have any other info at that particular point in time, you can just assume a north and figure out what the actual north is later. So bearing are then measured from the reference meridian. We call it the reference meridian. Okay, the directions that the north that we use sometimes is called the reference meridian. Okay, now how do they differ? Okay, in that figure or slide, it shows the Earth, okay, and shows the rotational pole. Okay, I think you know by now that the pole, the axis on which the Earth rotates is not exactly vertical, it's at an angle. So that north, okay, where the Earth rotates, is called the true north. Okay, and magnetic north is somewhere close to that, close to the actual north. Okay, the true north, but it varies. Okay, so from year to year, from time to time, okay, due to the Earth rotation and the magnetic field, the gravity, and it depends on which north we use. So if you are here, let's say there, if you refer to true north, your north will be that direction. But if you're there, if you're using magnetic north, the north will be that direction. And you can clearly see on that figure that there is a difference between true and magnetic. But it depends on where you are. If you're there, that's your true and that's your magnetic. There's also a difference, but not as much as before. Okay, so the difference between north and magnetic at any particular point on the Earth depends on where you are. So that's another slide, okay, to show the grid north, the relationship between the grid north and the true and magnetic. Okay, consider that the Earth, okay, that's the surface of the Earth, and we want to produce a map. Okay, we want to produce a flat, a plane, horizontal plane, onto a curved surface. Okay, so definitely the north for that one will be parallel to the side, okay, or to the grid. Okay, so if you're at point P, the blue line represents true north, the magenta represents magnetic, and the grid north is basically your coordinate system here. If that's your grid, so your north will be parallel to, like that. So obviously there'll be differences between magnetic and grid, as well as grid and true. Okay, even though it's not something significant when it comes to a small scale project. Okay, but when you're talking about long distances, it does make a difference. But anyway, just to give you an idea, if you are in this country anyway, if you look at a map published by the Survey Department or Jabatan Ukur dan Pemetaan, or JUPEM for short, there's always information at the bottom of the sheet just to show you the differences between magnetic north, grid north, and true north. Okay, so that's something I think for you to know. Okay, might not be what should I say too much concern at this time, unless of course you are involved in a project that requires that covers a lot of a big area, a vast area. But then we normally leave that to the surveyors because they are more specialized in this area. But anyway, just some info between the north, okay, the differences between magnetic, green, and true north. Okay, so how do we go about determining this direction, the north? Okay, true north, using a gyrotheodolite or GPS. So wherever you read from your GPS, it shows you north. That's the true north, the actual north. Magnetic north, using a compass, and grid north, using the map of the area. Okay, so that's a figure of a magnetic compass. Okay, that's which I think it's just a simple magnetic needle, rotating, show you where the north is. Okay, but this is with smaller graduations, the term is a surveyor's compass. And a gyrotheodolite. So GPS, I think you're familiar with that. Everyone knows what GPS is. Gyrotheodolites are equipment where you can actually find the direction of the true north. So you might ask, why bother with a gyrotheodolite when we have GPS? If you are on the surface, that's fine. You use GPS. But if you're, let's say, you're doing a tunneling work, okay, there's no GPS signal. So you need one of this. You need one of this gyrotheodolite to tell you where north is when you're when you are underground, when you do tunneling. You should don't want to end up with tunneling in the wrong direction. Okay, so that's another, what should I say, knowledge, another info that I think you ought to know. Okay, so you never know, one day you might be involved in tunneling, so you will come across, okay, a gyrotheodolite. So there's a grid north, okay, basically parallel to the north, to the northing, parallel to the side of the maps, or the grids, should I say. All right, and another coordinate system that used frequently in surveying is a polar coordinate system. Okay, nothing new. I think you've done this in your mathematics when you deal with complex numbers and so on. But here we're going to make use of that. We're going to call it polar coordinate system, which simply means that if you have a point B, okay, instead of giving a northing and easting to that, we're going to give it a distance and a bearing. So distance S and bearing theta. So that's polar coordinate. So if you look closely now, when you are in the field, okay, you're doing your traverse, you're measuring bearing to B, you're measuring distance to B. So in other words, the two values that you measured are in fact the polar coordinates of that point. So we're going to make use of that. Okay, we're going to make use of that coordinate, of that numbers, of that values to proceed with our calculation, okay, to get our coordinates. So in the field, we observe polar coordinates. So we will produce a map, a plan. The plan normally is in rectangular Cartesian coordinate. So when you do your traverse work, you will be dealing with converting rectangular to polar and the other way around. Okay, so when you're given a bearing, okay, you have to convert them to rectangular, and luckily enough, scientific calculators these days have this conversion facility, a standard function. So which means that calculations will be quite straightforward, and then easier to do, and I should say will minimize errors in the sense of getting the wrong quadrant. Okay, now let's do one example here. You find the bearing and distance of AB if the coordinates of A and B are given as such. Okay. All right. So I think the next slide just show the calculation needed. Okay. So we need to based on the coordinates given, right? We need to get the differences in northing. I call it delta and AB, and the differences in easting. So that's basically what the values are. Differences in that difference in northing, and that's the difference in easting. To calculate the bearing, you simply need that number, and you can easily obtain that by using a tangent function. Okay, and the distance, of course, using Pythagoras. You would, based on those two numbers, you're going to get your distance. Okay, it's quite easy and straightforward. Okay, but I'm not going to recommend this. Okay, because if you try to use sine, cosine, and tangent as they are, you might make errors in the sense that you might get the different quadrant. You might not get the right quadrant. Okay, so I think the next slide will probably explain.
انضم معنا الآن واشترك بالقناة ليصلك كل جديد. YSAG، معا نحو مستقبل مشرق.